Good morning, everybody. Welcome back from the weekend. It is now time to get into finishing up the class mode, right? You still have 2 homework assignments due, right? Chapter 13, chapter 14. Right? Finish strong there. The instructions for turning in your quiz sheets are flashing on the screen. I'll have this up today. I'll have it up on Wednesday. Some people get into a panic. Oh my gosh, I didn't turn them in on the day, Mr. Balogh. You can turn these into me until next Friday, right? So we're getting way ahead of the game here. The sooner you get them in, the better. Not only will you not forget, but also your grade in Canvas will become the most accurate, right? When I get the quiz scores in there, so on and so forth. Probably not going to be out of 50 points. I've fallen off the horse a bit in terms of giving out points. You just go and add up your totals. Go past 50, doesn't matter, right? Just keep going, but I'll probably only do it out of like 25 or 30 or something. Don't panic about it, right? And then, let's see, what else is there? Lab this week is going to be lecture. However, I think I'm a day ahead on the schedule. Like I was supposed to be finishing up chapter 13 today. Which means I can either give you a day off on Thursday, or I can just be here and have it be like grasp, right? Where you come in and just knock out your homework and that kind of stuff. So we'll see how far we get in fluids, but I'm pretty sure I can get most of fluids done by this Wednesday. Maybe a little tiny bit on Monday, and then we can really start reviewing next week, like kind of half of Monday and all of Wednesday for your exam next Thursday, right? And then, I forgot to look it up real quick. So our last meeting together, according to my calculations, is Wednesday, May 17th. So you're going to take the exam on May 11th. Okay, that's a Thursday. And then the next time we meet won't be till the following Wednesday during finals week. Because finals week, all the classes don't hold a regular thing. And we always go by the lecture schedule for finals, not the lab schedule. And so you'll come here for your test autopsy. You'll come to this room, 8 o'clock in the morning, Wednesday, May 17th. I'll keep reminding you of that. I still get people coming in on Monday or Tuesday going, what's going on? Finals week is different. All right. I'll collect those quizzes at the end. Here are the labs, and it's got the, you'll see just a check mark on the static problem solving thing. All right. I just put a check mark on the static problem solving sheet for your credit on that one. All right. Wow. Think about it. Your last chapter in Physics 4A. Right? You're excited, relieved, terrified, right? It's physics, right? And you've come a long way. You really have. I know some of you are still doubting, but you really have done a great job. We're going to tackle this last one. Of course, we're going to bring all of our toolboxes to bear on the problem when it comes to fluids. See, up till this point, everything that we've dealt with, well, okay, we started by making everything just point charges, right? It didn't matter if it was an armadillo, aardvark, a sheep, a penguin, and a goat. It didn't matter, right? It was just all the point object. And then, sort of more recently, we've started extending those objects. And we've had to take into account the lengths of objects and where forces are being applied and all that sort of stuff. And here, we've got objects that are constantly changing their mass and their shape. That's what fluids do. So one thing that you need to be aware of when a physicist says the word fluid, we mean something maybe not what you're thinking of, right? Because what's the fluid everybody thinks of when you say fluid? Water, right? And it's going to be our main example. I'll constantly use water because we're familiar with it. But realize that a fluid is any gas or liquid. It's a catch-all term that takes in both of those things. And I'm equally comfortable talking about the fluid that surrounds you right now as I am about the fluid that you might drink, right, in your morning coffee. Both of those things are fluids. They're both things that, they don't keep their mass the same. So like up till now, we've really kind of kept the mass of objects the same. Even in collisions, we would maybe combine a mass or maybe change where the mass is for moments of inertia. But it wasn't like mass was flowing places, and that's more or less the problem that we have when it comes to fluids. And so we are going to change just a little bit what we talk about when it comes to a fluid. So instead of mass, we're going to use density. And all of you that have taken chemistry can tell me what the volume mass density is. What is it? So now I know how many of you have taken chemistry or how many of you have chosen to forget that chapter in your life. It's too early in the morning. High school, right? It's just too long ago. Do you remember anything like this? The mass divided by the volume? Okay. That letter right there is not a P. That is the Greek letter rho. Okay? It's supposed to be sort of more fancy, but my handwriting's bad. It's kind of like a sort of a scripty, curly, flowy P. I don't know what it's right, but it's supposed to be the Greek letter rho. And it stands for mass density, volume density. So take total mass divided by its total volume. Now, key thing about density. It doesn't change, no matter how much of a material you have. So if I have a swimming pool's worth of water, and I have a drinking glass full of water, it's the same water, both of those things will have the same density. That ratio changes, right? So this applies to the density of anything. Density of aluminum. I could have a huge chunk of aluminum, and I take a little tiny chunk out of that aluminum. It's going to have exactly the same density because its mass changes in proportion to how much volume it takes up. This is really handy. This lets us work with fluids much the same way that we would work with a solid object. If the density doesn't change, then it really doesn't matter sort of how much fluid we have. But we can't answer the question, right? How much fluid went down the pipe? Well, if we're working in density, it's a pretty quick thing to be able to switch over, right? And solve for the volume if we know the mass, right, of the water that came down. So density becomes our method, our crutch, our standard. Instead of talking about mass, we're going to be talking mostly about density. The other thing that gets a little bit squirrely, and this one is a P, capital P, okay, is force. So when we're talking about forces, it was, again, always sort of about one object applying a force on the other. When it comes to fluid, if I go get the fire hose and I drag it in here and I start squirting you with the fire hose, number one, you'd be mad. Number two, you'd be cold. Number three, you would experience the force of, say, all of those water molecules striking you at different times, right? It's like this kind of constant flow. And so it becomes awkward to talk about the force, okay, of the fluid hitting you. And instead, it's better to talk about the pressure. Sort of a similar trick that we're pulling off with density here. We take a force and we divide by the area that force is applied to, we get something that's more consistent, that is independent of like the total volume or amount of fluid that we have, and ends up being actually a fairly simple relationship between how deep a fluid is and how much pressure it exerts. The thing about pressure though, notice that you divide by area, right? So for any given force, if we focus that force down to a really small area where it's applied, what happens to the pressure? it increases, it goes up, right? So we got to be aware, right? If we're kind of spreading out the effect of our forces, we could really lower the pressure. Or if we're concentrating the effect of our forces, we can really up the pressure. So these are again our trick here to be able to use some of our more familiar physics and toolboxes without having to deal with all the changing masses and changing forces that are around. All right, units of density. What are the units of density? What are the units of mass in the SI system? I mean, I know it's the end of the semester and you want to give up. Keep going. Keep going. It's okay. Kilograms. And then what are the units of volume? Meters cubed. Okay. And this is what we use in physics. We use kilograms per cubic meter because they are the standard SI units. For those of you who took chemistry or are chemistry majors, you do it wrong. Grams per cubic centimeter? No?
Milliliters, right?
Milliliters. Okay, fine. Milliliter is a cubic centimeter. So it even gets worse in chemistry. So, for example, the density of regular old water. In physics, we say it's 1,000 kilograms per cubic meter. In chemistry, they would say this is 1 gram per cubic centimeter, or as Adam pointed, 1 gram per milliliter. Okay? Those are all equivalent densities. Okay? But just beware. In chapter 14 here in physics, you want to use true SI units, which would be kilograms and cubic meters. You got to get to these units in order for the math to be able to work itself out. Pressure. What are the units of what are the units of force? It's a Newton, right? And then area. Good, meter squared. Excellent. Okay. This has a new name. Okay. This is called a Pascal. Capital P, lowercase a is the symbol. Okay. And pressure units are a little bit messed up. Okay. The Pascal is the SI unit of pressure, 1 Newton per square meter. But that came about later than other units that were being used that in a lot of ways feel a little bit more standard. So you may, if you've been in chemistry, you may have heard of the atmosphere. 1 atmosphere's worth of pressure. Okay. 1 atmosphere is defined as the pressure at standard temperature pressure at sea level. So remember, pressure comes about because of a force being applied over an area. At sea level, what pressure are we talking about, and why is it called an atmosphere? It's the pressure that is the result of the force. What force? Gravity. No. The weight of the air. Wait, air has weight? Does it have mass? Little bitty teeny tiny. So therefore it has weight. And therefore, if we add up the weight of a column of air that's directly above you, and you're at sea level, we would call the pressure that force of air acting on your area, we would call that an atmosphere. So it's a standardized number for a standardized sea level that doesn't in reality really exist. It exists by definition, not by practice. But 1 atmosphere is equal to 1.01 times 10 to the 5th pascals. A unit that you are probably more familiar with has to do with your car tires. Okay? When you inflate the tires on your car, and I hope you realize that you do need to inflate the tires on your car. Actually, we're coming in about probably the next 20 years or so, we'll probably transition away from air tires to tires that don't require air at all to function. But on the sidewall of the tire, it'll indicate sort of what you have to keep your tire pressure. Why do you want to keep your tire pressure up? What are the benefits? Safety is number 1. Number 2, Saves you money. Okay? If you maintain it at that number that says on the sidewall, you get the most bang for your buck, and you won't risk your tire flying off of your rim. What is the unit for that tire pressure? PSI. What does that stand for? A pound per square inch. All right. Well, it turns out 14.7 pounds per square inch is equivalent to 1 atmosphere's worth of pressure. So let's stop here and think about that for a second. The pound per square inch. So pounds is a unit of force, right? And the square inch in the stupid unit system could be an area. So it's still a pressure. But it's at atmospheric pressure, it's 14 points, so about 15 pounds for every square inch of area. And here at Fresno, we're approximately at sea level. We're about, 300-400 feet above sea level, right? So what does that mean for you? How much pressure are you experiencing right now, assuming we're at sea level? 1 atmosphere, or 14.7 pounds per square inch, or 101,000 pascals. Okay? So I now know why it was so hard to wake up this morning. I mean, think about it, right? 14.7 pounds for every square inch of surface area on your body. I don't expect anybody to know this, but do you know what the average surface area of a human being is? 2,000 square inches. It varies, of course, right? But that's the average. So 2,000 square inches of surface area, 14.7 pounds for every square inch. How do we find out how much force is acting on us right now? Well, solve for the force, right? We take the pressure times the area, so 14.7 and roughly 2,000 square inches per human being. I'm feeling the pressure and the force. 29,400 pounds. So approximately 30,000 pounds of force acting on you right now because the atmosphere weighs something. Why are you not crushed? Why are you not squished like Rick? No. Bones? No, bones aren't that strong. Spread out? Well, no, that's like, I calculated the total for you. If I took you back to the hydraulic press and I put you under 30,000 pounds of force, you would squish like crazy, right? Okay, so what's going on here?
The pressure is evenly distributed on all parts of your body.
All parts of your body, meaning?
Like it's coming in from all angles.
And? Nobody ever thinks of it. Okay. How much pressure is inside your body?
The same amount.
14.7 pounds per square inch. Okay, so you're old enough for this talk, right? But a mommy and a daddy love each other. You are conceived. You guys look shocked there for a second. You are conceived at 14.7 pounds per square inch. You're born at 14.7 pounds per square inch, and you mostly live your life at 14.7 pounds per square inch unless you do something dumb like go to the top of Everest or something, right? But more likely, you'll probably have jumped in a pool at some point. When you jump in that pool and you dive down to the deep end, what happens? You feel the pressure, don't you? Because when you dive down the bottom of the pool, if you're not wearing a scuba tank, you are doing what? What did you just do? You just closed all the holes in your body. That's what you did. When you're holding your breath, okay, you've just shut down all gas exchange between you and the rest of the universe, okay? which means that you have pressurized your body to atmospheric pressure, and now you dive down into the water. The water, being more dense than air, has a more rapid pressure change with depth. And so now you're down at the 6-10 foot mark in the pool, right? And what are your ears feeling like? You feel the pressure, right? You feel them squeezing in. Okay? So now there's a difference in pressure. And you can feel it. So the fact that we don't feel air pressure doesn't mean it's not there. What's probably more important is talking about the difference in pressure between things. As long as the difference in pressure between the inside and outsides of our body is zero, we have the same pressure inside as outside, we tend not to notice it, right? So 30,000 pounds inside pushing out, 30,000 pounds outside pushing in, everything adds up to a net force of 0. All right, let's talk about swimming pools in more depth. Too early. This might come as a bit of a surprise. You dive down to okay, I want to point out this person is not dead. I've been accused in the past that my stick figures look like they are lifeless objects. It's happiness down at the bottom of the pool. Okay? The extra pressure that you would experience diving down in the swimming pool, okay, only depends on the depth of the water you are in. This is a bit kind of mind-blowing and non-intuitive. Notice, I said it only depends on the depth, not the total amount of water in the pool. So let's try to tease this out. We'll start with sort of a definition here, right? Physicists spell depth weirdly. We call it the height of the column of fluids. Okay, sorry, we just do that. The pressure, okay, remember it's a force divided by an area, right? Okay, so that pressure that's added by the water. So how much pressure is there at the surface of the water? 1 atmosphere. Why is there 1 atmosphere of pressure up here? There's air up there, right? You don't swim in space. You float, but you don't spin, right? Well, actually, you don't even float because there's no buoyant force. So this extra pressure turns out to be rho times g times h. Oh, wait a second. Hold on a second. That's supposed to be pressure, right? Do the units work out? You can spend time on it. Don't just trust me. They do. The density times little g times h is a unit of pressure. And so, if we wanted to talk about what the total pressure you experience would be, okay, it would be equal to some sort of ambient pressure. This P naught is usually atmospheric pressure unless you are told otherwise, right? So it's going to be that atmospheric pressure plus the density of the fluid that you happen to be in, the planet that you happen to be swimming on, and the depth of the liquid, the height of the column. Notice, it doesn't matter if you're like standing up straight or lying down, as long as your head is at the same depth, right, the same height of water above you, the pressure is going to be the same. It doesn't matter how much water is in the swimming pool. All that matters, okay, is the depth of the column of fluid. And I guess if you're swimming in honey, you'd have to use the density of honey. But that's your business, right? I don't want to judge. Tenaya Lake. Tenaya Lake exists in Yosemite National Park. It's up at about, it's like 6,800 feet above sea level. Tenaya Lake is about, it's like 850 something feet deep. Okay? It's pretty deep alpine lake. Okay? But it's kind of small-ish. The lake's roughly the size of this campus. Okay? And so Tenaya Lake being small but fairly deep, right? So let's compare and contrast that with, is this hitting below the belt? You guys know what Tulare Lake is? The lake has reformed in the Central Valley. It's flooding Corcoran and several of the communities down there, right? It's horrible. That lake dried up in the 30s and 40s as agriculture started booming, right? The lake is back because we've had a lot of rain and snowmelt and all that kind of stuff. Now, Tulare Lake is so big that when you're standing in Corcoran, the shores of Corcoran, nobody expected to say that for a while, you can't see the other side of the lake. The lake stretches from horizon to horizon. Okay? It's really big, okay? But the average depth is something like 3 feet. So it's really shallow. So you got this huge lake that's taking up a big part of the south part of the San Joaquin Valley, right? But it's only 3 feet deep. So which of these lakes experiences more pressure at its bottom? Tenaya Lake. The not very big but very deep one compared to Tulare Lake, right? Which you can't see the other side of. It's a bit non-intuitive. We want to assign like amount of fluid, like the total volume of fluid to the pressure, but that's not how pressure works. So that, okay, does anybody know what that is? Anybody know? It's a dam. You know which dam it is? Yeah, the Hoover Dam. Okay. Hoover Dam was built to be able to hide the Allspark. So that's Lake Mead behind it. Okay. Lake Mead. So Lake Mead doesn't look like that anymore. Anybody know what Lake Mead looks like now? Dry lake, almost dry, right? You heard that they've been finding bodies as the lake level goes down. Okay. And the bodies all show signs of violence associated with the organized mobs in Las Vegas in the 30s and 40s. Lake Mead was a popular dumping spot. Okay. Anyway, that got dark real quick. But the lake level's been falling. But prior to the lake level falling due to climate change, right? The Hoover Dam is approximately 800 feet from top to bottom and holds back the entirety of Lake Mead. Lake Mead would stretch back for about 120 miles behind it. A great, fantastic water source for Las Vegas and parts of Arizona and other parts of Nevada. Why am I talking about this dam? Let's just say, that you take a garden hose, right? Lots of garden hoses, right? You screw them together, and you get 800 feet of garden hose, and you run it down the face of Hoover Dam, okay? So that you have a garden hose that's exactly the same depth as the water is on the other side of the dam. And then you start filling your garden hose with water you plug up the bottom, right? And you fill up the garden hose, right, with water. The pressure at the bottom of that garden hose, 800 feet down, would be exactly the same as the water pressure 800 feet down on the other side. That's bonkers, right? It's like, come on, Mr. Bale, that can't possibly be right. And I'm about to show you and prove to you that it is. But to be clear, I'm not talking about the total pressure on the face of the dam, right? From all that water behind it. I'm talking about going down, swimming down 800 feet, right? To the bottom and talking about the pressure that you would measure because of the water over there versus the water. Now, this experiment actually can't be done in real life because a garden hose cannot, it'll burst, okay? Before that hose is like 1/10 full or something like that. You'd be exceeding pressure. But let me show you in a video, okay, how much the actual shape of the water makes absolutely no difference. It's only the depth, the total vertical depth, the height above an object, that determines the pressure.
This is an electronic pressure gauge with a pressure sensor at the bottom. Flowing into the sensor through a tube increases the pressure and drives a bar graph display whose length is proportional to the pressure at the sensor.
What they mean is they've calibrated it.
Show how the pressure in a column of water changes with increasing depth.
They've calibrated it so that the lights always light up at the surface of the water.
The display shows that the pressure increases in direct proportion to the depth. What will happen to the display if we tip the water column at an angle?
Okay, so that display, right, has been calibrated so that the LEDs always light up at the point where the water level is, right? And so the deeper it goes, the more LEDs light up, right? So as it went down, the pressure went up. So he's going to take that entire tank and he's going to tilt it over at like a 45, 50 degree angle, okay? What I want you to do right now with your neighbor is just tell them whether you think that bar of light, the pressure gauge, is going to go up, go down, or stay the same. Go. Tell them why, too. Alright. Alright, show of hands. How do you say the pressure gauge gets longer or shows increased pressure? No? How many says stays the same? Oh, interesting. And so how many of you say it's going to get shorter? Oh, there's like a slight majority on shorter. Okay, shorter. Defend your position.
H is changing.
H is changing. The actual height of the water is changing. Is the total amount of fluid changing? No. He's not going to dump any water out, right? It's just going to change the height. So let's see who's right. Let's see who's right. Uh-huh. Watch carefully.
Tipping the column of water reduces the pressure reading. The length of the display is still equal to the vertical depth of water above the sensor, as shown by this line.
Does there need to be actual fluid above the sensor? No, right? All that mattered was the vertical height between the surface of the fluid and where that sensor was, right? Like I said, it's a non-intuitive result. Like you wouldn't just sort of start off guessing, oh, that's the way pressure works. But that's the way pressure works. So if I go swimming 10 feet down, right, in a swimming pool, right, and then I swim, say, 4 feet down inside the ocean, where do I experience more pressure? In the pool. Why? Because I was deeper, right? Assuming both of the pool and the ocean were at sea level, right? So hold on to that, right? Just believe it.
How do water towers work?
We're going to talk about that a lot, but yes. How do they work?
Yeah.
They work very well, thank you. Water towers take water and put it up high, okay? And by putting that water up high, so a water tower does not store water. It is not the city's water supply. It's the pressure supply. They pump water up there so that the pipe coming down, right, has a height so that they can supply water pressure to the town. Okay? They're taking advantage of this idea, right, that the more depth of fluid you have, okay? And the reason it's a tower, like the reason there's a big tank on top, is because if water were to stop flowing in for any reason, there'd be enough water to maintain water pressure until they fix the problem to get the water back in, right? We don't have a lot of water towers here in Fresno. Water towers tend to get replaced as your population density goes up. They're replaced with pumps that just supply the pressure. But for a smaller town, the pump can be used to just bring the water up. That's a lot more efficient. And then that height of that water tower provides water pressure for the entire town. Did that answer your question? We're going to get way more detail. Promise. But before that, we got to talk about how hydraulics work. Anybody that's ever been to the mechanic for any reason has probably seen one of these. What does it do? It lifts the car up, right? It magnifies force by taking advantage of pressure. Let me see if I can't explain what's going on here. A hydraulic is any system that uses pressure to magnify or reduce forces being applied to things. Usually we're trying to magnify them, but sometimes we do need to reduce them. So Pascal's principle, Blaise Pascal was an Italian mathematician, natural philosopher, sort of a prototype physicist in the age before Newton. And he discovered this particular sort of property of fluids, and so we name the principle after him. So what I'm drawing here is it's kind of a funny shaped tank, and the tank has it's got like an input and an output. It's got two places to pour fluid in, and in this tank, what we're going to do is we're going to put a couple of movable pistons, like little platforms. Okay, one of them's quite large and the other one's quite small, right? So we've got, say, area 1 over here, okay, like a cross-sectional area that maybe is measured in centimeters, really tiny, right? And then we have an area 2, which could be this big disc, right? And then we fill the system with hydraulic fluid. For our purposes, hydraulic fluids are incompressible. In fact, at Physics 4a, we always assume whether it's water or honey, whatever fluid they're talking about, we're not going to worry about what happens to the volume of the fluid as it experiences more and more pressure. Most fluids work well at normal standard pressures, but if you really start squeezing on a fluid, it's going to change its volume. Its density is going to change. We're not going to worry about any of those density changes. We'll assume ideal fluids. Okay. So we fill it with hydraulic fluid. Real hydraulic fluid has this feature. It really doesn't compress hardly at all under normal operating circumstances. All right. And then what we're going to do is we're going to apply a force. We're going to apply a force to one side of our hydraulic system here. And what we want to do is we want to try to calculate what sort of force we get out from the other end. At first glance, you're like, well, Newton's third law, right? Like, come in, force is equal and opposite, right? Force in, force out. But what Pascal discovered is that inside of this fluid, Pascal's principle states that the pressure everywhere in that fluid stays the same. And if you try to exert, say, more pressure on side 1, you'll immediately have that same pressure at side 2. This lets us do we're not breaking physics, but we're taking advantage of the relationship between force and area that pressure is. So remember that pressure is a force divided by an area. And so we can write that down for both sides. And if we want to know how much force we're getting out, let's say the big side, we can rearrange and solve. So F2 is going to be area 2 divided by area 1 times force 1. And let's just say that our force we put in the other side, I'll do it in pounds for you. Pounds is more, and an engineer just walked by, so I better. She didn't hear me. Okay. Let's say we put 10 pounds of force in, okay, on that side. And I'm just kind of making up numbers. Let's say area 2, okay, is 100 times bigger than area 1. So I don't know what the actual areas are, but I know that the ratio of the areas, right, is 100. So if that's the case, and I solve for F2, well, that's going to be area 2, which is 100 times area 1, divided by area 1, so the areas cancel out, times my 10 pounds. And what's 100 times 10? That's 1,000 pounds. What just happened? We were able to take a small force and make it a big force. by taking advantage of Pascal's principle, which is the principle upon which all hydraulics function. If you've ever been in a vehicle or own a vehicle where it's like a hatchback where the back part of the car comes up, you've heard the hydraulic pistons working there. Okay? You open it up, it goes psss, right? I always wanted it to sound more like Star Trek. They just sort of sound like metal, right? But there's two, you look for them, there's two rods, okay, that are right there, and the rods have another cylinder over them, okay, and anybody whose hydraulic cylinders have failed on their hatchback knows exactly how heavy those things are, right? Like it could be really hard to lift them open if you didn't have that extra hydraulic help, okay, in order to open the door. Anybody that's ever had to jack up a car, okay, you know that you can put that jack and you can start pumping and maybe 20, 30 pounds of force on that lever, right? But you're lifting a 3 or 4 ton vehicle, right, off the ground. But we don't get away with it for free. There is a cost to this. What's the cost? We're getting 100 times more force out. So where do we pay the price? Those of you that have ever jacked up a car. The force is small, right? And we get a bigger force out. How far do you have to move the jack handle? So the jack handle, right? You're swinging this thing up and down like maybe through 3 or 4 feet of displacement, right? Okay? And for every push, right, you push down, how much does the car go up? Never. It feels like never. You could go up and down for like 4 miles over here and you only get like 3 inches out of this side, right? You pay a price in distance. We can't disobey conservation of energy. And so the amount of work, we're getting more force out, right? The amount of work has to be the same. We pay a price in distance. So basically, if we have a factor of 100 here, we have to move the small one 100 times further than we get motion out of the big side. Okay? Now, obviously, it can be a lot more complex, and you can do some more tricks, and get some more multiplication out for less distance, blah, 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 blah. And that's what these systems at repair shops do. That's what systems in our doors do. Some of these doors, I think those might be hydraulic, but sometimes there's springs and they're just hiding, right? But hydraulics are everywhere, and they've really changed. Any big piece of machinery probably has a hydraulic pump on it in operation somewhere. So you can get big forces out of little ones. All right, so that's Pascal's principle. We're doing good. This is great. Okay, Archimedes. Heard of Archimedes? No? No? I'm surprised. He seems like something that the current generation of Instagram and social media would really just be familiar with, because he was an influencer. As a matter of fact, he is credited, I don't know if credit is the right word, with the world's first recorded wardrobe malfunction. No, you don't know this story? What is wrong with the American education? Okay, Archimedes. Did Archimedes screw? Helped the Greek nations fight off the Romans, blah, blah, blah. Figured out, okay, have you heard the story of whether or not the crown was lead or gold?
Yeah.
Okay, so this is Archimedes' story, okay? So there was some high boss, mucky-muck king, whatever it is they called him in ancient Greece, right? They just offended all the Greeks in the room. And the king had a crown made. There was some suspicion as to whether or not the crown was actually made out of gold, or maybe it was just lead that was painted over with gold, right? So king goes to Archimedes being this smart guy and famous and all kinds of stuff, influencer, and says, can you please tell if my crown is made out of lead or gold? And Archimedes, I don't know that this happened, but I imagine this is how the discussion went, right? He's like, Archimedes is like, well, yeah, melt it. If lead comes out, it was made of lead. I don't think that's probably the answer that the king was looking for, right? The king wanted a non-destructive way in order to in order to find out if the crown was lead or gold. So Archimedes did what any rich, aristocratic Greek noble of the day would do when presented with a problem that needed some thinking time and some discussion. What did he do?
He took a bath.
Took a bath. Okay? He took a bath with a capital B. What was the Greek and Roman bath culture like? Where do we get the dimensions for the modern day Olympic swimming pool? The ancient Greek and Roman baths. Okay? These were the center of Greek and Roman culture. In an age where you couldn't do Facebook or post something to Instagram, right? This was the place that you went to socialize, to discuss, to wrestle, to swim, do a whole bunch of things. Matter of fact, you went down, and it wasn't just, I'm going to go take a bath. No, you took your entourage. Like you went and installed yourself for like 3 days, right? And you brought all your servants. Somebody has to peel the grapes, right? Like it was this big thing, right? And so, as the story goes, Archimedes went to the bath and he's discussing philosophy and the nature of the problem, and he's sitting there in a quiet moment, and he's staring at the surface of the water in the pool, okay? And people are getting in and out, okay, of the water. And he's watching. It's well known, okay, that the more people you have in the pool, the higher the water level would go, right? And if all the people got out, the water level would go down, right? So he's watching this happen, right? And he's just sort of in that moment, right, of contemplation and thinking, and maybe his mind's wandering a little bit, when all of a sudden, like a lightning bolt straight out of Zeus's hand, right? He gets it. Like he makes this cosmic connection between the water level going up and down in the pool and the reason that people float when they're in the water. And he is so excited. Have you ever been like so excited or like figured something out and it just hits you so hard that you can't talk? You're like, oh my God, ah! That was Archimedes. He was so excited. He jumped up. He started running out of the bathhouse, screaming at the top of his lungs, Eureka! You know what Eureka means? I have found it, or aha. Okay? The problem was he had forgotten his toga. So, old white guy running down the street naked. Now I have your attention. Greek and Roman culture didn't put as much of a importance on modesty as we do in our modern age, right? But it was still kind of weird to see somebody running down the street naked yelling Eureka, right? But then people are like, oh, Archimedes. What was it that Archimedes had discovered? It's now known as Archimedes' principle, okay? And this is what it is. The force that causes objects to float. When you get into a pool, you feel weightless. You feel as though gravity has kind of been canceled out. What is that force called? The one that lifts you up when you're in a fluid? Buoyancy. It's called the buoyant force. A buoy is something that floats on the top of the surface of water. So that buoyant force, we'll use capital B as our symbol for it, okay? We'll get back to the crown here in a minute, I promise. That buoyant force is equal to the weight of the fluid that got displaced. Okay, let's untangle some words there. What does displace mean? Move or push out of the way, right? So if I jump into a pool and I'm completely surrounded by water, I displace my volume's worth of water, right? I've got to push that much water out of the way. The water has to make room for me, right? Okay? So If I'm only floating with half of my volume submerged, then I'm only displacing half of my volume's worth of water. That word displacement means to push out of the way. So what Archimedes has connected is this idea of the force that pushes up on you because you're in a fluid with the weight of that fluid that got pushed out of the way, that got displaced out of the way. So, but how do we write down the weight of a fluid? What's weight? We know it as mg, right? Okay. Well, how do we find the mass of a fluid? What do we use instead? Density, right? But we can't just kind of go, well, it's rho g. No, that doesn't have the right units, right? So we got to find a way to write the mass in terms of the density. Well, density is a mass per volume. So that means a mass is going to be a density times a volume. And I can come over here then and shove that mass in there, and I get a weight of rho v, and the little g comes along for the ride. Now, for whatever reason, I was taught, and I see written in textbooks, rho gv. I think it rolls off the tongue just a little bit better, rho gv, as opposed to rho vg. Do whatever order you want. I like that order. Okay? But Archimedes' principle, the weight of a fluid that gets pushed out of the way is exactly equal to the buoyant force, the lifting force on an object when it is in that fluid. That was his big aha moment. That was the big connection that was going to enable him to figure out whether or not the crown was lead or gold. But he's discovered something even more profound than a way to figure out jewelry problems. He's discovered why things float. So what is floating? What does that mean for something to float? Or like what's implied? It's probably like when you think of a floating object, like your brain goes first where? A boat, right? Okay, so boat on water, right? By definition, the boat's working if the boat is where? On top, right? Would we agree? Okay, there's an exception to that called the submarine. We'll get to that boat in a second. But most boats, right, are happy boats. Supposed to be a boat, if they are floating on the surface of water. But the entire boat is not submerged in the water. It's just a portion of the boat is submerged in water. How much of the boat is submerged in water? Exactly the right amount. Sounds like a physicist's answer, right? Not an engineering answer. Okay, because there were no numbers involved. How do you know it's exactly the right amount? Because it's floating. So what does it mean to float? You know something now that you know chapter 12. This is a static equilibrium condition. You're like, Mr. Balogh, fluids were nice up until now. Now you've ruined it, right? Now we're static equilibrium. It's okay. Right? The boat has weight, right? But in order for it to be floating, by definition, not accelerating, okay? Not getting higher in the water, lower in the water, not sinking, not doing that kind of stuff, right? What must be true about the buoyant force? It has to be equal in magnitude, opposite in direction, to the weight of the boat. So, if your boat has a weight of 1,000 pounds, what is the buoyant force acting on it? 1,000 pounds. What if you put 500 pounds of cargo in the boat? Now how much is the buoyant force acting on the boat? 1,500 pounds, right? Can you sink a boat by putting too much cargo in it? Yes. Barges on the Mississippi have this happen every once in a while. They load them too much, and if you exceed the ability of the buoyant force to apply, what limits the buoyant force? What does the buoyant force depend on? Volume. Volume of what?
Water displaced.
The displaced fluid. That's kind of the key thing to remember here about Archimedes' principle. This is the density of the fluid displaced, right? This is the volume of the fluid that is displaced. And yet, I'm trying to talk about it in the context of a boat. So you can overload a boat. If there's a maximum volume that can be displaced, which is the volume of the boat, right? If you go past that limit, if you put a load in there so that the total weight of the boat is more than the maximum buoyant force can be, that boat will be sinking. So buoyant force depends on the fluid that you are in. So if you're floating a boat in water, that's different than floating a boat in honey. Don't do that. Depends on the planet that you're on. Little g. And it also depends on the maximum volume of fluid that can be displaced. That's your limit. So one way to kind of play around with this a bit is for any object that is floating. We know that the total sum of forces has to add up to 0. Which means that we know that the buoyant force and the weight are opposing each other. Which means that the buoyant force has to be equal to the weight. And since the buoyant force is equal to rho g times v, and I can rewrite the mass of any object as how? Its density times its volume. So this is mass of the object times g times the volume of the object. This is density of fluid, volume of fluid. This means that I can, well, first of all, what cancels? Little g. What did we just discover? The result of whatever's about to happen works everywhere. Surface of planet Earth, the moon, Saturn, Jupiter, Venus. What does it take to float an object? As long as the volume of the fluid is equal, I did it bad. It's supposed to be density of the object. As long as the volume of the fluid that gets displaced is equal to the density of the object divided by the density of the fluid times the volume of the object. This is one of many ways to write something that you already know. Okay? Then this object will float. In other words, what does the density of an object need to be in order for it to float? What happens if I throw iron in water? What does it do? It sinks. But if I throw wood in water, what does it do? It floats. Why? Which one's more dense? The iron. Okay? If the density of the object is less than the density of the fluid, what sort of number do we have right here in this ratio? It's less than 1. Meaning that the volume of fluid required is less than the volume of the object. And if the volume of fluid is less than the volume of the object, can the object float? Yes. But what happens if the volume of fluid required is bigger than the volume of the object? Will that thing float? That thing will sink. And that will happen when the density of the object is bigger than the density of the fluid. This ratio right here of densities tells you the ratio of the volumes. In other words, if your object is half as dense as water, how much of that object is going to be above the surface? Half. How much is going to be below? Half. But what if your object is, 90% that of water? How much of that object will be below the water? 90%. The average density of the human body is between 95 and 98%. Okay? You can actually change it by inflating your lungs or emptying your lungs. You may have done this in a pool, right? You jump into the pool and all of a sudden you go, ooh, bounce up at the top, right? And you go, right? And you start sinking, right? What you're doing there is you're changing the volume without significantly changing your mass, right? So you're altering your density. But for an average human being that's just sort of floating in water, about 96 to 98%, which means, right, that we need to have approximately 97% of our body below the surface of the water for us to be floating. Which is why you're taught in swimming and rescue swimming and all that kind of stuff that if you're tired and you need to just float, you're supposed to lay on your back. Why? Hopefully you can get the 3% that's this above the water, right? Without expending any energy. Let's watch some demonstrations. I do these on video because they're very messy. And I like to poke fun at before graduate students ever asked to film them. Does he look like he enjoys his job?
Yes.
This demonstration will show how the buoyant force on a submerged object is related to the amount of water displaced by the object. This aluminum cylinder and tail hang from a scale, which shows the total weight to be 29 newtons.
No smiling, this is physics.
We'll lower the cylinder into this water container, which has an overflow spout.
Notice the water level's right at the spout level. Be careful. If you smile.
When the cylinder is submerged, the reading on the scale decreases to 20 newtons. All water displaced by the cylinder will flow into a beaker.
You watch that. No smiling.
If we pour the water that was displaced by the cylinder into the small bucket hanging from the scale, how will the reading change?
Okay. The water that's in this beaker over here is exactly the volume of this cylinder. This cylinder displaced an equal amount of water. Okay? Does the cylinder and the water have the same weight? No, they are different materials, right? They're different densities, okay? But note it, do you remember what it was like 29 being weighed in air? And then it was 20 when it was in water. Where did the 9 newtons go? In other words, what's the buoyant force acting on it? 9. Where did that 9 newtons come from? Came from the weight of the displaced water. How much does this weigh? 9 newtons. So if he takes that beaker now and he pours it into the bucket that's also attached to the scale, what should the scale do? Should go back to 29. Don't you smile. This is serious science stuff. No smiling. No fun. No. That was almost a smile. You got a drip there. It's okay. We won't look at that.
The scale now reads the same as before the cylinder was lowered into the water. The buoyant force on the cylinder is equal to the weight of the water displaced.
Archimedes principle.
We'll use these 3 blocks of wood to demonstrate how density affects the depth at which objects float. This block is cut from balsa wood, with a density of about 0.14 grams per cubic centimeter. When placed in water, it floats with only about 1/7 of its volume submerged. This is a block of pine, with a density of about 0.5 grams per cubic centimeter. It floats with about half of its volume submerged. This is a block of ironwood, with a density of about 0.9 grams per cubic centimeter. When placed in water, it floats with about 9/10 of its volume submerged.
So can you guess what the density of water is? It's got to be 1, right, on that scale. Because if something has half the density of water, half of it floats, right? Half of it's above, half of it's below. All right. I'm going to show you this next video, but not for the reasons that you think. I'm going to show it to you. The subject's kind of interesting, a little bit stupid. Watch what happens near the end. Prepare to be shocked.
We're used to seeing objects floating in large amounts of water, but how much water is actually required to float an object? We'll use this wooden block to find out. This container is just barely larger than the block and has a small amount of water in the bottom. When the block is placed inside, a small amount of water is enough to float the block.
Surprising. Okay, fine. Get on with it.
The amount of water required to float an object is just enough to actually surround the object in its container.
All right, now watch.
In a container of the right size, a large object, such as this ocean liner, could also float in a small amount of water.
What just happened? Now, you have to understand something, okay? These clips that I've been showing you, okay? They come from a set, well, anciently of DVDs, right? There were, I think it was 32 discs in the set, okay? And on each disc, there were maybe 15 to 25 of these videos, right? So we're talking hundreds of videos, right? I've watched them all. Right, okay? And nowhere, anywhere in any of these videos is anybody smiling. Nobody. Serious science. Right? You just, I get the feeling that the producer's like, no smiling. Right, okay? Can't look like you're having fun. Just students, torture, right? And then this happened. I haven't. So this is how video designers and graphic designers crack under pressure, right? It's so serious, all this editing, blah blah blah, and then they hand it off to the animation team, like, hey, we need an animation of a big disembodied hand picking us, right? I'm not sure the producers knew. I think those little people got inserted by whatever graphic designer had decided they had had enough. And they were going to put some humor somewhere in about 289 episodes worth, right? I saw that, I fell out of my chair. I couldn't believe it, right? It was just like, what the heck was going on? Anyway, floating objects. Why would we want to know how to float an object, say, on Venus? Do you know what Venus is like? It's a hellhole. Literally. It is hot enough to melt lead on the surface of Venus. Venus's surface pressure is like 400 times our own atmospheric pressure. Its heat runs into the close to thousands of degrees Fahrenheit. Okay? Why does Venus have such a terrible surface? They let climate change get out of hand. Let that be a lesson to you. I'm not lying. Venus is very much like Earth. It's about 93% the size of Earth in terms of its volume and its mass, so it's roughly the same density. It exists in the habitable zone around our star, which means liquid water can form there. It is slightly closer, so it gets a little bit more energy, and that might have what pushed it over the edge. But at some point in Venus's past, they had a runaway climate catastrophe, which caused Venus's atmosphere to become primarily carbon dioxide with some other gases in there. And as you know, carbon dioxide is a warming gas. And so that means solar radiation that hits Venus gets trapped like a blanket under that carbon dioxide. And so Venus's surface temperature, which we're pretty sure was pretty close to what Earth's was back in the day, right, ran out of control to the hot, super dense atmosphere that you see today. Now, I am not saying that you driving your car is going to cause that to happen here on planet Earth. That's not going to happen, okay? We are going to have bad effects from climate change, and we're all experiencing that now. What, it was 98 a day ago, and it's supposed to be like 60 tomorrow? That's the weather for you, brought on by climate change. But if we want to go to Venus, it's really hard to design a lander that can put up with that amount of pressure and that amount of heat for very long. The Russians did manage to land 2 craft on the surface of Venus in the 1960s. Nobody else has tried since. That's how bad it is. And the Russian landers lasted for like 10 minutes, right? Which was pretty amazing. Currently, there are plans to send missions to Venus to not land on its surface, but to float in the clouds. There are areas in the atmosphere of Venus that have exactly the same pressure as we have here on the surface of planet Earth. And it just so happens the temperature at that altitude is a little bit chilly, a little bit on the chilly side. We're talking like Alaska winter chilly, okay? But the pressure is correct, the temperature is a little bit low, there isn't very much oxygen there, so we would need oxygen tanks. But if you had a balloon, you could send the balloon to the Venetian atmosphere, you could actually float in the atmosphere and not be exposed to the sulfur rains, the acid rains, and the pressure and the temperature at that level. When we come back on Wednesday, we will tackle the problem of the crown, okay? And see whether or not the king's crown was indeed made of lead or of gold. And then we'll learn about how balloons work and work our way into Bernoulli's principle. If you have your quiz sheets and you want to turn those in, just bring them up to the front, put them in a table, on a pile right here. Make sure your name's on there. Make sure that you have all of these things that are on the screen on the front of your page.